Hey, so this is problem 6 from 2-2, and I just want to talk about this method a little bit. What's good to recall is in this chapter we have two methods that are introduced, the Euler-Lagrange method and the integrating factor method. Now, when do I use these, and do I need to use either of them? Well, the integrating factor is a pretty good catch-all if you're unsure how to find a particular solution or a homogeneous solution. You can use the integrating factor since this is a first order equation, right? We can see it's first order because of this. And it's linear in y, which is also very nice. So dy dt, and then a y, and then we have some functions of t here. So both of those are free game. Now, the Euler-Lagrange, though, what's the benefit of that one? Well, if we had a 0 on the right-hand side, it would be a little bit more straightforward to solve this, right? And so we can get the homogeneous solution. And then the Euler-Lagrange is really a method for finding a particular solution. So in this case, so even that would be overkill. We could use it, but if we can think of y, right, as some function of t that would make the left-hand side just equal to the value of t, then that's a particular solution. You're done, right? So Euler-Lagrange is really there to help you find particular solutions. In this case, if we just say y, though, is a half, we get a 0 plus 2t times a half, so plus t. So that would just be equal to t. So this y being 1/2 is a particular solution. So we could just use that. We don't need Euler-Lagrange. So let's just hold on to that as our particular. So then all we have to do is, to get our general solution, we would solve the homogeneous version of this and then use our superposition principle. So how do I get a homogeneous solution here? Well, let's rewrite this and do separation of variables. So dy dt is equal to negative 2ty. Because I can write it like this, let's bring everything with a y to the left and everything with a t to the right. And then let's integrate both sides. So if we just integrate both of these, the left-hand side gives us the natural log of y, right? And the right-hand side gives us negative t squared plus some constant. And so as we get y is equal to, well, right, we can write it the long way, although we're going to get used to being able to do a few things. This is sort of the absolute value of y, but then through a few very common moves that we're going to do, this whole thing then reduces simply to, maybe I'll do it in yellow, y is equal to some arbitrary constant times e to the negative t squared. Great. Now looking back up, we had a particular solution, and this solution we just found is our homogeneous solution, right? So in order to get the full general solution here, we'd say y, maybe we'll do this in blue, different color. Y then will be the particular and the homogeneous added up, so some constant times e to the negative t squared plus 1/2. And there you go. There is the general solution. So another way of saying that is any solution, any function y that can make this equation work must be able to be written as you see here.